right, let's kick things off with a big question for you. What do your pen, your hand, and a star that's billions of miles away, what could they possibly have in common? The answer, believe it or not, is that they're all made of the exact same fundamental stuff. These incredibly tiny particles called atoms. They're the building blocks of, well, literally everything. And that's exactly what we're going to break down in this explainer. The amazing world of atoms and molecules, the absolute fundamental building blocks of our entire universe. So let's start right at the beginning. What even is an atom? Turns out people have been wondering about this for a very, very long time.
You know, this idea isn't new at all. I mean, way back around 500 BCE, an Indian philosopher, Maharishi Kanad, had this theory that if you keep splitting matter, you'll eventually hit a particle you just can't split anymore. He called it parmenu. Then, about a century later, a couple of Greek philosophers, Democritus and Leucippus, had the same exact idea, and they called it atomos, which literally means indivisible. Wild, right? That set the whole stage for modern chemistry centuries later.
And when we say these things are tiny, we really, really mean it. The radius of just one atom is about a nanometer. That's a billionth of a meter. It's hard to even wrap your head around that scale. Here's a great little trick for your exams. Nano has a 9 in it for 10 to the power of -9. So, as scientists started digging into this stuff, they discovered two super important rules that everything in the universe seems to follow. You can think of them as chemistry's two golden rules. Okay, so the first one is the law of conservation of mass. It's simple. Mass can't just be created or destroyed during a reaction. You get what you start with. The second one is the law of constant proportions. This just means that a compound, say water, always follows the same recipe. Always. The ratio of its ingredients by mass never changes. Let's make that first law super clear. Imagine you put 10 grams of stuff, we'll call it reactant A, on a scale. Then you add 20 grams of reactant B. The total is 30 grams, right? Well, after they react and create a totally new thing, product C, it will weigh exactly 30 grams. Nothing just disappears into thin air. I love this little saying. It's a great way to remember it. Mass is like a true friend. During a chemical reaction, it never, ever changes. The amount you start with is the amount you finish with. Period. And that other law, the law of constant proportions, just as reliable. It doesn't matter where you get your water from, a river, your kitchen tap, a fancy expensive bottle, it makes no difference. The mass ratio of hydrogen to oxygen will always be 1:8. It's like a cosmic recipe that never, ever changes. Okay, so you've got these two huge laws floating around. It was time for someone to put all the pieces together. And that someone was a scientist named John Dalton, who came up with the first modern atomic theory. Dalton's theory was a total game changer. He basically gave us the first real rule book for atoms. He said, yep, everything is made of atoms, and you can't divide them. He also proposed that all atoms of one element, like gold, are identical, and atoms of different elements are, well, different. And crucially, they combine in simple, whole number ratios to make everything around us. This was huge. But here's the cool thing about science, right? It's never finished. Dalton's theory was brilliant, but it wasn't perfect. We later figured out that you can split the atom into even smaller bits, protons, neutrons, and electrons. And we also found things called isotopes, which are atoms of the same element that have slightly different masses. But this isn't about Dalton being wrong. It's just how science works. We build on ideas and make them better as we learn more. All right, enough history for a bit. Let's get our hands dirty and talk about how chemists actually work with all this stuff. It's time to open up the chemist's toolkit. So trying to weigh an atom in grams is, well, it's just not going to work. They're way too light. So chemists came up with a clever solution, the atomic mass unit, or AMU. Just think of a fruit seller who uses a standard 1 kilo weight to measure all their fruits. For chemists, our standard weight is the carbon-12 atom. We define one AMU as exactly 1/12 the mass of that carbon atom, and then we measure everything else against it. Okay, listen up, because this next bit is a total lifesaver for your exams. If you need to figure out the approximate atomic mass for the first 20 elements, there's a super simple trick. If the atomic number is even, just double it. If it's odd, double it and add 1. Just make sure you memorize those 4 little exceptions and you're pretty much set. Of course, that trick is only useful if you actually know the elements right. So we've got you covered. Here are 2 fantastic little memory aids for elements 1 through 10. hi, hello, listen to BBC News on Friday night. And for 11 through 20, Na Mongo Abdul say Pepsi Soda Cola are Kaju Cutly. Seriously, screenshot this. It'll save you so much time. All right, next step is a word that sounds a little technical, valency. But don't worry, the idea is super simple. It's just the combining power of an element. Basically, it tells you how many chemical bonds it likes to make. This table shows some of the most common ones you'll run into, all grouped by their valency. And once you know the valencies, you can unlock this awesome trick called the crisscross method for writing formulas. It's so easy. First, you write down the symbols and their valencies. Then, you just crisscross the numbers, not the plus or minus signs, and they become the little subscript numbers for the other element. And if you have a group like OH, just pop it in brackets if the number is bigger than 1. Bam! CaOH, 2. Simple as that.
Okay, so we're getting pretty good at this. We can write formulas, but how do we count atoms in, like, a glass of water? I mean, there are trillions upon trillions of them. We need a better way. And the solution is a really powerful idea called the mole.
I know, the name mole sounds like a weird little animal, but in chemistry, it's just a number. Seriously, that's it. Think of it like this. You know how a dozen always means 12 eggs or 12 donuts or 12 whatever? A mole is just like that. It's the chemist's dozen.
And what is that number? Well, get ready for it. It's called Avogadro's number, and it is gigantic. It's 6.022 times 10 to the power of 23. That is a 6 with 23 zeros after it. It's an enormous number, which is perfect for counting enormous amounts of tiny, tiny atoms.
And this chart, this is where it all clicks. This is the key. Right at the center, you have 1 mole. Now, follow the path up. You see that 1 mole of carbon atoms is simply 12 grams of carbon. That's its atomic mass, just in grams. Now, follow the path to the left. You'll see 1 mole of anything contains that magic Avogadro's number of particles. The mole is the bridge that connects the invisible world of single atoms to the real world of grams that we can actually weigh in a lab. So, I want to leave you with a final thought. A little challenge. A single drop of water has about 1.67 sectillion molecules inside it. It's a mind-boggling number, but now you have the tools to understand it. With Avogadro's number and this idea of the mole, can you figure out how many moles that is? Give it a shot. That right there is the power of chemistry.